For a long time, astronomers believed that they had a fairly accurate understanding of the origins and evolution of the universe. But then, the James Webb Telescope was launched. Webb is detecting more and more phenomena and objects that are hardly compatible with our models. How could galaxies be almost as massive as our Milky Way today, just a few 100 million years after the Big Bang? Why is the cosmos expanding much faster in reality than it should theoretically be? And why does the observation of galaxy rotations lead to the crazy assumption that our cosmos is embedded in something even bigger? Today, we'll show you which mysterious Webb discoveries are keeping scientists on the edge of their seats, and why some of them believe it's possible that our universe is by no means the only one. When the James Webb Telescope plunged into the depths of space on December 25, 2021, experts had given it an overarching goal. It was to revolutionize our view of the universe. And today, 4 years later, we know that the $10 billion device is rising to this ambitious task with flying colors, albeit in a way that researchers would probably have preferred to do without. Developed specifically for infrared astronomy, Webb is examining, among other things, the first luminous objects and galaxies that formed after the Big Bang and the subsequent Dark Age. However, the things Webb detected triggered an astronomical earthquake for the simple reason that they were in stark contrast to what had been expected beforehand. Experts actually believed that they had a comprehensive understanding of the evolution of the cosmos. After the universe exploded into existence some 13.8 billion years ago, it took several 100 million years for the first galaxies to form. However, these were significantly smaller and less massive than their later counterparts, which seems logical given that there was less normal matter available at that time. The early star clusters were thought to be chaotic, unfinished, and simply structured, more reminiscent of cosmic construction sites than fully developed galaxies. The fact that the universe has been expanding continuously since its birth has also been known for a long time. A combination of cosmic background radiation, supernova observations, and galaxy distributions provided consistent data on how fast the universe is expanding in detail. However, there were discrepancies between the actual observations in space and the theoretically predicted value of this so-called Hubble constant. But most researchers assumed that these differences would disappear with more precise Webb data. Even the distribution of mysterious dark matter, which scientists use to explain the movement of visible matter, seemed to be well described by rotation curves. According to these curves, early galaxies were expected to exhibit turbulent movements, structures that were not yet fully ordered, and above all, too little mass to explain rapid rotation without dark matter. In short, we believed we knew the basic features of cosmic history. Although not every chapter had been fully deciphered by any means, our findings seemed comprehensive enough to rule out any major surprises. And that is precisely why Webb's discoveries came as such a shock. From then on, we were confronted with things that, according to our understanding, should not actually exist. How Webb is shaking up the standard model. It all started with 6 inconspicuous reddish points of light in a section of the sky near the Big Dipper. Closer analysis showed that the luminous structures represent very early galaxies that existed just 500 to 700 million years after the Big Bang and turned virtually everything we thought we knew about galactic evolution on its head. Instead of the expected baby galaxies, researchers were looking at surprisingly large and massive representatives that absolutely no one had anticipated in this form. According to the data, all 6 galactic premature babies comprise more than 10 billion, and in one case even more than 100 billion solar masses of stars. However, since according to our models, there was not enough normal matter at that time to form such impressive structures, the galaxies became a real problem for science and earned themselves the infamous nickname universe breakers. What no one expected at first, however, was that this was only the beginning of a series of similarly perplexing Webb discoveries. In the aftermath, JADES-GS-Z14-0, another galaxy that existed just 290 million years after the Big Bang, was detected, and once again, it appeared far too bright and star-rich. The matter became even more puzzling when Webb found evidence of oxygen here, which, conversely, means nothing less than that several generations of massive stars must have already formed and died at that time. Equally remarkable, however, is MOM-Z14, which is another 10 million years older and is just as astonishingly luminous. The role of dark matter in all this should not be underestimated either. Basically, it acts as a kind of invisible scaffolding in the early universe. It pulls normal matter together and forms halos in which stars and galaxies can grow. Without this additional cosmic glue, the development of stable galaxies in such a short time would be hardly conceivable, and that naturally raises questions. Does dark matter really function as we believed it did in this early era? Or do we really need to rethink the galaxy formation processes from scratch? What is certain is that Webb is turning our previous understanding of the evolution of the universe upside down, and that ever greater doubts are being raised about the established standard model of cosmology. The cosmos is expanding too fast. However, this is not only due to the impossible early galaxies, it is also because the universe is not doing what it should be doing on paper in other areas either. As mentioned briefly earlier, the universe is not a rigid, unchanging structure. It is a construct that has been expanding steadily since its creation. It's important to note, however, that the universe is not growing into an existing space. Rather, it's space itself that is becoming larger and larger. But the cosmos is not expanding just any old way. As astronomers in the 1990s were surprised to discover, it's actually expanding at an increasing rate. The driving force behind this accelerated expansion is again considered to be dark energy, which, like dark matter, has not been directly proven experimentally. The crucial question now, of course, is how fast the universe is expanding, and experts can determine the corresponding speed using the so-called Hubble constant. But this is also precisely where the problem lies. While the Hubble constant is around 67 kilometers per second per megaparsec, according to the standard model, real observations in space have yielded a significantly higher value. In detail, measurements based on supernovae, gravitational lenses, variable stars, and red giants yielded a value of 73 kilometers per second per megaparsec. But what is this so-called Hubble tension all about? Could it be that the previous data was marred by distorting measurement errors? Well, that's exactly what the researchers led by Nobel Prize-winning physicist Adam Rees wanted to know when they re-examined the real value of the Hubble constant a few months ago. To do this, they used data collected by Webb over a period of 2 years, and ultimately came to the sobering conclusion that the expansion puzzle had been confirmed once again. The evaluation of the most comprehensive Webb dataset to date also yielded an overall Hubble constant of 72.6 kilometers per second per megaparsec. This makes it increasingly unlikely that the discrepancy is due to measurement uncertainties. But how can it be explained? Well, primarily by the fact that our knowledge is incomplete. It's possible that something is missing in our understanding of the early universe, such as a component that gave the cosmos an unexpected impulse after the Big Bang. However, previously unknown properties of dark matter, exotic particles, or primordial magnetic fields are also suspected of causing the deviations. An astonishing Webb discovery. Is our universe located in a black hole? To top off the expansion puzzle, new analyses conclude that we have been measuring the expansion of the universe incorrectly all along. The culprits are Type 1a supernovae, the standard candles of cosmology to date, which are one of the most important tools for determining distances in space. In stark contrast to the common assumption, however, new studies have shown that these supernovae do not all shine with the same brightness. Instead, supernovae in younger star populations appear to be fainter than those of old stars. And when the measurements are corrected against this background, it becomes apparent that the expansion of the universe is not accelerating, but has apparently already slowed down. But this also means that dark energy, as the driving force behind this expansion, cannot be constant. Rather, it appears that its effect is gradually weakening. And if these results are confirmed, they would mean nothing less than a radical paradigm shift in cosmology. The standard model would have to take another blow, and we would have to admit once again that we are still far from fully understanding our cosmic home. However, this does not only apply to things within our home, but perhaps also to those outside it. But how can that be? After all, the cosmos literally encompasses everything. Or does it? Well, not necessarily. Some researchers believe that our universe is merely a tiny link in an infinite chain of universes. No less exciting is the idea that our universe is located inside a black hole. And here's the kicker. An observation by the James Webb Telescope may actually indicate that we are in fact hidden in the belly of such a bizarre mass monster. In detail, researchers at Kansas State University evaluated the direction of rotation of a total of 263 distant galaxies and uncovered an unexpected pattern. One would expect a random universe to have an equal number of galaxies rotating in one direction and in the other, but this is simply not the case. Instead, 2/3 of the structures studied rotate clockwise, while only 1/3 rotate in the opposite direction. There are two ways to approach this rotational imbalance. The first is that we are simply dealing with a result of the Doppler effect, and thus with a kind of optical illusion. But the second, and this is the exciting part, explains the phenomenon by saying that our universe originated in a black hole that passed on its axis of rotation and preferred direction of rotation to us. What initially sounds like a crazy idea is actually compatible with what is known as Schwarzschild cosmology. And what this implies could not be more exciting. On the one hand, our entire universe would then be the interior of a black hole in a larger parent universe. And on the other hand, every mass monster in our world would embody the gateway to another baby universe. And the button below our video represents the gateway to a new subscription. Simply click on the thumb and subscribe to never miss another post from us. See you soon.